Hi guys. So today I want to talk about some patterns I noticed on the LeetCode linked list problems. So I noticed that there were 4 patterns that seem to repeat across multiple problems on LeetCode, which have to do with linked list. Also, there's one technique. So before I bring to you those 4 patterns which I noticed, let's take a quick recap on what a linked list is. So singly linked list is where every item has a next pointer to the item ahead of it. Doubly linked list, there's a back pointer also, front and next and previous, where you have a reference to the next and the previous item. So when would you use a linked list? So this is where the LeetCode part starts. So if you have to recognize that this is where I want to use a linked list, when would you use a linked list? So suppose you have a requirement where you want to be able to insert or delete in constant time, and you want to maintain the order. So you want to maintain this order in the list of items, and you want to be insert and delete from anywhere in constant time. What I mean by that is, suppose I want to be able to remove 2, or I want to be add items here. So all of that should be constant time and the order should be maintained. So maintain order, insert, delete constant time, and no need to resize. So those are the scenarios where you will use a linked list. So to understand why linked list is useful, you'll have to look at an array. So suppose instead of a linked list, I had an array. Suppose I have 1, 3, 5. Now if I want to insert an item, I'll have to resize the array. 1, 3, 5, 6. Right? So I'll have to create a new array, copy all the items over and add at the end, which is big O of n, because I have to go through all the items. Similarly, if I want to delete, if I want to delete 5, I have to again copy over the array 1, 3, 6. So if you use a linked list, in both these cases, you don't have to resize it or copy over. You can just like take it out, that would be delete, put it at the end, how many ever items, that is add. So and they are all constant time. So if you want or maintain order, insert, delete constant time and no need to resize, that's where you would use a linked list. So in LeetCode, the linked list problems are a little different from what you would observe in a real world linked list. So if it's a real world linked list, like if you see the Java implementation, you do not get a reference to the node. You can only do operations on the linked list itself. You cannot do operations on the node. If you give access to the node, in a well-designed linked list will never give an access to a node, because if you give an access to a node, you can mess up the invariables of a linked list. But in this case, for LeetCode, that doesn't matter. In LeetCode, they always give you a reference to the node. So now, having got that out of the way, let's see the few patterns that I've noticed in LeetCode linked list problems. So first pattern is merge two sorted lists. So these are 2 sorted lists, and you want to merge these 2 sorted lists to come up with a final sorted list. So the way you do it is, so here actually I'm using a technique which I'll point out later, and this is again a pattern that will come across many problems. So the way you do so notice here the first linked list is ordered 1, 2, 4. Second one is also ordered 1, 3, 5. Now to merge these 2 together, what we do is first we declare a dummy node. Okay, and we have 2 pointers to it. One is a dummy pointer and a current pointer. So it will be something like this. List node dummy equal to new list node -1 and list node current equal to dummy. So once I do these 2 lines, basically this is what I end up with. So what you get passed in is these 2 lists, and with these 2 lines I have a dummy node and 2 pointers to it. Now how do we go from here? So the way we do it is, we compare, so we have a pointer to the first element of both the linked lists. We see which one is smaller. Okay, so here I compare, left is 1, this is 1. If they're equal, I'll just take left. And then what I do, I will take the current, put its next equal to this. So these are the steps. First, recognize which one is smaller, then point the current nodes next to that node. Then you move the current and the one to which you're pointing. So current will come here. I'll just say C for current. Current will come here and left will come here. Now again repeat. Compare these two. Which one is smaller? This is smaller. So current's next, which is this guy, you will point here. Your current's next you will point. Then you move the current to current dot next. So C will come here. And then whoever you pointed to, that one moves ahead. R. Now again same thing. Compare these two. This is smaller. So current's next, point to that one. Move current over there. So move current over here. And then left will move one ahead. Again, compare these two. Which one is smaller? 3 is smaller. So current's next. So this one's next. You point to that smaller item. And then once you point the next to that, current equal to current dot next. So C points to this one, and then you move that one ahead. Now again compare these two. Which one is smaller? 4 is smaller. So you take current and do current equal to current dot. First point current to this, and then current will become current dot next. So current will come here, and left will become left dot next, which will become null. Now once one of them, so you do repeat this until both left and right pointer, neither one is null. Once one of them becomes null, you just point the currents next to that, and then the algorithm is done at that point. Current dot next is this, and there it's done. So if you notice, you have 1, 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5. Now you might notice there is this extra pointer here from the dummy, right? Which is okay, because what I'm going to return in the code is dummy.next. Dot next, which is this guy. Now this is an important technique which you will see many linked list problems can use this technique to reduce the amount of code. So let's look into that part also. So why did I do like this? Like, why did I create a dummy node and have its next point to this instead of directly starting the current at this? So even if you started the problem, solving the problem where you find the smaller node and point current directly to that, that will also work. But you'll end up writing a lot more code, because first time you have to say current equal to that smaller node. And once current is set, next time onwards, you'll have to do current dot next equal to the smaller node. So there is that conditional check. Okay, so that adds to code. And that can come in multiple places, because you don't know, like there are problems where there are multiple places where the first node can be set. So everywhere you'll have to add that check, that if it's not set, then this point to this, otherwise the next is what points to this. So and now you might ask, right, this extra dummy node, would that not create a problem, because my final result is going to be actually like this, dummy No, it won't create a problem, because what you return is dummy.next and there is no back pointer. So this technique only works for singly linked list. If it's a doubly linked list, this data structure would be wrong, because from here you'll come back to here, right? So then it will be wrong. So only if you're using a singly linked list, this technique works, where you have a dummy node which next pointer points to the first element, and you always return dummy.next, which is this one. And you cannot come back because there is no pointer backwards. So the place to use it again is if you have to return set and return head. So this is our head in this case. If you want to set and return head, and you want to avoid conditional checks where if it's null then point to this, if it's not null the next is going to point to this. So in cases like that is where you use this. An easy way to remember is anywhere you have to set and return a head, that is one place where you create a dummy pointer and return dummy.next. Just remember that much. If I have to return head, create a dummy pointer which points to the head, and create a dummy pointer whose next points to the head and return dummy.next. And this only works for singly linked list, not for doubly linked list. So that was first pattern. Now let me go to the second pattern. Now the second pattern. Second pattern is reversing a linked list. So reversing a singly linked list. One easy naive solution is to put them all in a stack and then pop them from the stack. So that is an easy way to reverse it. There is a faster way. So if you check the running time, there is a faster way to do it. So the faster way to do it is with 3 pointers. So the way you do it is you have a current pointer, let's just call it C. You have a previous pointer, let's call it P. So this is currently null. And there is a next pointer, let's call it N. So the way you go about this is first you take the current pointer and do its next equal to previous pointer. So in this case it will become null. So the current's next equal to previous. So that becomes null because previous is null. Then you move previous to the current pointer. So previous will point to whatever the current is pointing to, which will be like this. Previous will point to whatever current is pointing to. Current will point whatever next is pointing to. So from left to right, we just start moving the pointers. Current will point to whatever, say I don't have a next pointer at this point, but since I had taken this reference before, I can use that. So C will point to whatever this one is pointing to, is this guy. Now this guy himself will just do whatever it's pointing to dot next. And then it will become like this. And we'll point here. Now again we do the same thing. Take current and do its next pointer to whatever P is pointing to. So you cut this off, whatever current is pointing, his next pointer points to whatever P is pointing, like this. Okay, then starting from left to right, you move them all to the right. So P will point to whatever C was pointing to. So remember that here I'm not using dot next because this guy's dot next is pointing to null. I'll point P to whatever C was pointing to. So I'll take P and then it will be P will point to whatever C was pointing to. C will point to whatever N was pointing to. So C will point to whatever N was pointing to. Now N himself will point to N dot next because see this next reference is still there. So N will point to N dot next. So N will point here. Again repeat. C's next will point to whatever P is pointing to. So this dot next once you do that, you start moving all the pointers. Now P will move to whatever C is pointing to. So you say P is here. And then C will point to what N was pointing to. And N will point to N dot next, which is null. So N is gone. Now again, C's next will point to whatever, so it's next, whatever P is pointing to. So then you do this. Now you move them ahead. P will move here. And C will point to what N is pointing to, which is null. So, and you stop your algorithm at the point current points to null. So once this points to null, you return P. And now you have a reversed linked list. So you did this in one pass. So now let's look at the next pattern, third one. So the third pattern is find middle. So the way you go about this is you'll have two pointers, a slow pointer and a fast pointer. So the slow pointer will point to the first item, fast will point to the next item. And then what you do, your algorithm will progress this by 1, this by 2. Then again this by 1, this by 2. And at any point where fast becomes null, that's when you return the slow pointer, and that will be your middle. So let's try it out. I start like this. Move slow by 1 and fast by 2. So slow will point to this. Slow will point here, and then fast I'll move by 2. Slow by 1, fast by 2. So fast will come 1, 2. Then again move slow by 1, fast by 2. Slow by 1, fast by 2. And like I said earlier, whenever fast becomes null, you return. So first you move here, and when you do 2, it becomes null. So here it's null, and fast points to null. So that's when you return slow. But remember, you have to first move slow, then fast. So this point, when fast becomes null, you return slow, and that is your middle element. So that is find middle. Now let's look at the fourth and last pattern. And the final pattern is when you need access to nodes in between. So this is not a hard and fast pattern, but this is something like a thinking pattern. So like these are the problems where I've come across this among many more, where you need to access nodes in between, or some other form of access to nodes which is not like the head or tail pointer, somewhere in between. So things like that, you should when you see a problem where you have to access random nodes, you should step back and think for a second, like, could I use a map here, like a map of an integer to a node? Or can I use a list of nodes? Or can I use a priority queue of nodes? So those are places where if you try to solve directly by just using pointers, you might end up in a very complicated situation where it's very hard to solve. So when you ever see any access to nodes in between, or some other ordering of nodes, or where you need to access nodes where it's not accessible by first or last pointer, you should think of using either a map or a list or a priority queue or a set. So that is something to consider. So these are the 4 patterns. For the very first pattern, I had said where you use a dummy pointer to point to the head. So in the description below, I have put code for a problem where one I have used dummy pointer, and another one where I did not use dummy pointer for the pattern 1. And you can see without using a dummy pointer, the code almost becomes double. So let me see if there's anything else I wanted to talk about. Yeah, I think that's about it. All right, thank you.